All right, let's look at some vector applications. So in the last video, we talked about fundamentals of vectors, so how to work with vectors, add and subtract them, break them into components, find magnitude, direction, all those kind of things. So if you haven't seen that yet, or you're not familiar with how to do those things, go watch that video first. In this video, we're going to be looking at velocity vector applications. So these are the chapter titles here. In the next video, we're going to be looking at force vectors. So let's go ahead and jump in with an overview of vector applications. So when we're working with vectors, we just want to ground our understanding in our intuition. So here's a picture of a river. Let's say that you go to the river with your friend, and your friend is going to go inner tubing. And let's say that we know that the velocity of the river is, I don't know, let's just say 4 miles per hour. So the river's flowing at 4 miles per hour downstream. Your friend's going to go ahead and hop in an inner tube right here, and your friend can paddle at a speed of 3 miles per hour in this inner tube. And so we just want to intuitively figure out how fast your friend is traveling. So from where we're at right here, maybe we're in a helicopter looking down on the situation. And let's say that your friend hops in the river and starts paddling downstream with a velocity of 3 miles per hour. Well, from our perspective in the helicopter, if we geometrically add these vectors together, we're going to see the overall speed of your friend, right? Your friend is going to be paddling at 3 miles per hour, and then the river is going to be traveling at 4 miles per hour. So overall, your friend is going to be traveling at 7 miles per hour downstream, right? That's easy enough. Let's say, so again, the current is at 4 miles per hour. And let's say that instead of paddling downstream, your friend forgot something upstream and starts paddling upstream at 3 miles per hour. Well, from our view in the helicopter, if the river's flowing downstream at 4 miles per hour, and then remember when we add vectors together, we always start one where we ended the last one, so tip to tail. So if the current is downstream at 4 miles per hour, and let me actually change the color on that so it matches. So 4 miles per hour downstream, and then your friend is paddling upstream, so in the opposite direction at 3 miles per hour. Well, we have a current of -4 and your friend paddling at +3. So then the resultant vector is your friend is going to be slowly moving downstream at 1 mile per hour. Right, so that's all pretty intuitive. But what happens in this situation? So let's say, again, that the current is traveling at 4 miles per hour. Let me get a straight arrow there. There we go. So the current is traveling downstream at 4 miles per hour. Your friend is paddling 3 miles per hour, but your friend is paddling directly across the river at 3 miles per hour, right? So in this scenario, if we want to see the result of what's happening, we're just going to add the vectors together geometrically, right? So your friend is paddling to the right at 3 miles per hour. The river is flowing downstream at 4 miles per hour. And so the result that we would see from the helicopter is your friend would appear to be traveling in this direction from the helicopter, right? So your friend is traveling kind of diagonally across the stream because as your friend swims to the right, the current is pushing your friend downward. And so your friend is traveling along this resultant vector right here. Well, all right, cool. So if we wanted to quantify what's happening here, we could say that the velocity, whoops, let me change back here. We could say that the velocity that your friend is paddling, so I'll just call this V friend. So the velocity that your friend is paddling plus the velocity of the current of the river is going to equal the result that we see. Right? So in other words, velocity of your friend plus the velocity of the current equals the overall result that we see. Right? And then we could quantify each of these if we go back to breaking them down into their I and J components. So in order to figure out where your friend is actually traveling, how fast is your friend traveling, and in what direction your friend is traveling, we would say, all right, well, let's first break down your friend's velocity vector into its I and J components. So your VF, V friend, is going to be equal to, since your friend is paddling 3 in the positive I direction, it's going to be 3I. And then your friend is not paddling up or downstream, so that's going to be a 0J. And then we want to quantify the current, so our VC is going to be equal to, well, the current is not going left or right, so that's 0I. And it's going downstream by 4 miles an hour, so -4J. And then with this heading right here, and it's a good idea to kind of start out with something like this because this tells us how we want to now work with the vectors, right? It's very easy to get bogged down in the details of the components, but if we have this kind of leading the way, we can go back and say, what are we doing? Oh yeah, we want to add these two vectors together. And when we do, we'll get this result. So the result that your friend is traveling, our VR in this case, is going to be 3 plus 0 is 3I. 0 minus 4 is negative 4j. So now this is how we would describe the vector that is the result of your friend paddling in the river and the current of the river itself. Now, if we want to know how fast is your friend traveling, we're just going to find the magnitude of this vector, right? And so we just want to remember from the last video that we would find a magnitude of this vector by taking the square root of the I component squared, so 3 squared, plus the j component squared, so negative 4 squared. Right? So then we run all the math here, so we get 9 plus 16 is 25, and then we take the square root of this, and remember that it's only going to be the positive results because magnitudes are only positive. And so then the velocity that your friend is traveling is 5 miles per hour. I should say the speed that your friend is traveling is 5 miles per hour overall, right? 3 of those miles per hour are coming from your friend paddling to the right, 4 miles per hour are downstream with the current. And so together in this configuration, your friend is actually traveling at 5 miles per hour. And then of course, if we wanted to find the angle that your friend is traveling, it's going to depend on our reference. But if we find the angle right here, if we call that theta, then we're going to say that our theta is equal to the inverse tangent of the j component, so negative 4 over the I component. And then we could solve for that theta value, and that would give us the angle relative to what is the direction that your friend is paddling, right? So that's essentially how we're going to work with these vector applications. So let's get into some more details. Now, when we talk about direction, since we're dealing with velocity vectors, there are a couple direction types that we want to be familiar with. There's the classic unit circle angles, which is 0, 90, 180, 270, 360 degrees. So we can get problems that have these sorts of directions. We can also have cardinal directions, so north, east, south, and west. And the way that we work with these, so you might see something that says that something is traveling, let's say north, and we'll say this is north bearing 15 degrees east. So the way that we read these cardinal directions is whatever comes first is going to be the primary direction of travel, right? So in this situation, whatever we're describing is mostly traveling north, but there's a 15-degree offset to the east. So these second two things, they come as a package, right? So the way that we would chart this then is we would say that the direction of travel here is mostly to the north. So we'd say from the origin, it's mostly to the north, but then there's a 15-degree offset to the east. So this direction of travel is actually going to look like this, where there's a 15-degree angle right here, right? So this is how we would describe a cardinal direction. Now, we want to be able to relate cardinal directions to unit circle angles, because when we do the math, when we work with the math of the vectors, we're going to be using unit circle angles. So for example, let's say that we're given a direction. So I'm going to give a new direction just so we can practice. Let's say we're given a direction of west bearing 30 degrees south. Well, that means that the primary direction of travel is mostly west, but there's a 30-degree offset toward the south. So the direction is going to look something like this, where here is a 30-degree angle. Now, when we translate this to vectors to be able to work with, vector components and all of those things, we're actually going to think of this as what is this relative to 0 degrees, right? So we'll draw this over here. And thinking about what is this angle relative to 0 degrees, well, it's going to be 180 degrees to get to here, plus this 30-degree offset. So this angle right here is actually going to be 210 degrees. So when we work with it, we'll work with it as 210 degrees. Now, you might ask, how do we present our answer? So like we do all this math, and then we go to present our answer. How should we present the direction of our answer? Well, we should present our answer in the way that we're given information. So if we're given all information in unit circle angles, like in degrees, present your answer in regular unit circle degrees. If we're given information in cardinal directions, then we want to present our answer in cardinal directions. Let's look at some examples to make that make sense. So here's a problem that says, a jet maintains a constant airspeed of 500 miles per hour north, bearing 45 degrees east. The wind is blowing at 80 miles per hour north, bearing 45 degrees west. And then we're asked to do a series of things with that information. Now, what we want to understand is what kind of information are we being given here, right? Because what we've seen is this is just like the river problem that we were just looking at. So if we find the velocity of the jet, so just what the jet would fly in still air, so what the jet can do on its own, or in other words, the air speed of the jet, if we add that to the wind speed, so the velocity of the wind, so if we put those two things together, so here's the jet flying all on its own, here's the wind pushing up against it. If we add those things together, we get the results of how the jet is actually flying relative to the ground, right? So that's what we're going to be asked for, is stuff relative to the ground, right? So this is just like what we were looking at before, where like the jet is kind of like your friend paddling, the wind is kind of like the current of the river, and the result is what we see from the helicopter. All right, so let's start to break this down a little bit. So part one says express the velocity of the jet relative to the air. And so what that's asking for, it's saying take the velocity of just the jet relative to the air. So ignore the wind for right now. We're just going to think about the airspeed of the jet, and we're going to break it down into its I and J components. That's going to be the first step. And in many of these problems, that's going to be the first step, is breaking down each of the vectors into I and J components. Well, to do that, let's read this information that we have here. So it's saying that the jet maintains a constant airspeed. So the speed of the jet relative to the air is 500 miles per hour at a direction of north bearing 45 degrees east. So I just want to sketch that real quick. So I'm going to think about, okay, here's north, here's east. So the main direction of travel is north, but there's a 45-degree offset to the east. And by the way, that's going to be the maximum number here, is 45 degrees, because if this number goes any higher, then the primary direction of travel has changed. Okay, so we've got north bearing 45 degrees east. So technically that's a 45-degree angle here. But since we're going back to unit circle values, we're going to analyze this as a 45-degree angle relative to 0 degrees. So this is our 45-degree angle here, right? So it's 45 degrees. The magnitude of this is 500 miles per hour. So that's what the jet is looking like. And so we want to break this into its I and J components. So to do so, we can say that the velocity of the jet is equal to, and this is where we'll just do the magnitude times the directional information. So 500 times the cosine of 45 degrees for I, plus 500 times the sine of 45 degrees for J. And then we'll simplify that. So the cosine of 45 degrees and the sine of 45 degrees are both root 2 over 2. So then this becomes 250 root 2. I probably need a little more space here. Uh-oh. That's not good. Well, 250 times the square root of 2, I, plus 250 times the square root J, right? So there's that information there. Now we want to find the velocity of the wind relative to the ground. So we're going to take this information and similar approach. So I'm going to first diagram the wind. So the wind is blowing north, bearing 45 degrees west. So that's a 45-degree angle right there. We want to relate this to our unit circle values. So 90 plus 45 means that this angle is actually 135 degrees. So when we're looking at this, we're looking at it as 135 degrees. And the magnitude is 80 miles per hour. So then we can say that the velocity of the wind is going to be equal to this magnitude, 80, times the cosine of the angle, so 135 for I, and then the magnitude, 80, times the sine of 135 for J. All right, cool. And then we'll simplify this. So the velocity of the wind, if we plug this into a calculator or just know our unit circle values, this is going to be cosine of 135 is negative root 2 over 2. So this is going to end up being negative 40 root 2 I. And then the sine of 135 degrees is positive root 2 over 2. So this is going to end up being 40 root 2 J. Okay, cool. So part 3 says find the velocity of the jet relative to the ground. So we just want to keep in mind what we're doing, right? So we said that the overall approach to this is if we find the velocity of the jet and add it to the velocity of the wind, that's going to give us the resultant velocity, right? So what we'd see the jet doing relative to the ground. So that's what this is asking for. It's saying find the velocity of the jet relative to the ground, or find the resultant vector. So we're just going to add these things together. So the vector here is going to be 250 root 2 minus 40 root 2 for I. So we just added the I components together. And 250 root 2 plus 40 root 2 for j. Now this is the vector that describes the jet and the wind all together, right? So now part 4 says find the ground speed and actual direction of the jet relative to the ground. So what we're going to do now, the concept here is let's take this vector information and let's find the magnitude of this vector, and then let's find the direction of this vector. So the ground speed is saying what is the speed of the jet relative to the ground. And where we get that is by adding the airspeed of the jet plus what the wind is doing, right? So to do that, we're going to say, all right, well, the velocity of this vector is going to be equal to the square root of the I component stuff squared. So 250 root 2 minus 40 root 2 squared plus 250 root 2 plus 40 root 2 squared, and that's all under this square root. So when I do that, I get, let's see, I'm going to say VR is approximately equal to square root of, let me just set all that up, and let's see, I got about 296.985, I'll call it, I'll round it there, squared plus, and then let me do this side here, 250 times the square root of 2 and 40 times the square root of 2, and I'll add those two things together and we get about 410.123. So 410.123 squared, and then I'll go ahead and square that, and I'll square my previous answer, that 296, that squared, and then add these things together and take the square root, and we get an approximate value. So the approximate ground speed of the jet is 506, we'll call it 506 miles per hour. We'll go ahead and just round it there. So it's about 506 miles per hour for the jet. So that's part of it. Now this other part says to find the actual direction of the jet relative to the ground. So to do this, I just want to sketch this vector. So I want to sketch this resultant vector. And when I sketch this, I don't have to be super accurate, or I should say I want to be accurate. I don't have to be super precise. So what that means is when I sketch this vector, I just want to know, is I going to end up being a positive number or a negative number? Since I ran the calculation down here, I know that I is going to be a positive number. So I'm going to sketch it going to the right. And if I wanted to label it, I would just label it 250 root 2 minus 40 root 2. And then I'll sketch the j vector. So I definitely know that this is going to be a positive number. So it's going to be going up this way. And if I wanted to label it, I would label it 250 root 2 plus 40 root 2, like that. And so those are the components of the vector. The actual vector, the resultant vector, is going to be what happens when we connect the original origin to the tail over here, to the terminal side. So this is what the actual vector looks like. I'm looking for this angle right here, right? So I'm going to say then tangent of theta is equal to the j component, 250 root 2 plus 40 root 2, all divided by, let me clean that up a little bit, 40 root 2, all divided by the I component. So divided by the I component is 250 root 2 minus 40 root 2. And then I'll let my calculator run all this and take the inverse tangent. So we'll go ahead and do that. So that's going to be that 410 number divided by that 296 number. And then I'll take the inverse tangent of that, and I'll get a theta value of approximately 54, I'll just call it 54.1 degrees. Now, I need to know how to interpret this, so I'm going to go back to what cardinal directions mean. So if this is a 54.1 degree angle here, then my primary direction of travel is to the north up here. And then I just want to subtract 54.1 from 90 degrees to figure out what this angle is right here, right? So the purple angle is 54.1. If I subtract that from 90, I get a value of approximately 36 degrees. We'll just call it 36 degrees. We'll round it there. So this is a 36 degree angle. So that means that the direction of the jet relative to the ground is going to be, maybe I won't say theta because I labeled that over there. So the direction of the jet is going to be north, bearing 36 degrees east. So from the ground, it looks as though the jet is flying at 506 miles per hour, north, bearing 36 degrees east. Okay, cool. So that's that problem. Let's see what's next. So next, okay, so this one, similar setup, but a different approach. So again, we want to be aware of the information that we're given and the overall concept. So this says you are poolside lounging, listening to your summer DJ Khaled Slaps playlist, when you notice a plane flying overhead at 620 miles per hour due west. We'll talk about frames of reference in just a second. You also notice the warm summer breeze blowing through the palm trees at 50 miles per hour east, bearing 30 degrees south. Suddenly, your best friend, the pilot of the plane, calls you in a panic to say all of the plane's navigational systems need to be reset immediately. Your help is needed. All right, so then we're going to tell your friend what the airspeed indicator on the plane should be reading and what the compass on the plane should be reading. So let's think about what's happening here. We know that with these vectors, with these types of velocity vectors, if we take the velocity of the jet and we add the velocity of the wind, we get the resultant velocity. But let's just take stock of the information that we have and what we want to find. So this says that you are on the ground when you notice a plane flying overhead at 620 miles per hour due west. So this information right here is what you are seeing from the ground. So this is the resultant vector, right? This is, you're on the ground watching the plane fly, and what you see is a result of the plane flying and the wind blowing against the plane. So you see the resultant vector. All right, so then the problem goes on to say that you also notice the warm summer breeze, the wind, blowing through the palm trees at 50 miles per hour east, bearing 30 degrees south. So that's this information here. All right, so then your friend wants to know what should the airspeed indicator on the plane be reading and what should the compass on the plane be reading. So that means that we need to solve for the velocity of the jet, right? And all the things that go with it. So this is our goal, is to solve for this. So if we look at just this arithmetic here, if our goal is to solve for Vj, we know Vr and Vw, then the way that we're going to approach this is to subtract Vw to the other side. So here's what we're after. We're going to find the velocity of the jet by finding the resultant velocity vector and subtracting the velocity of the wind. This is our overall template for what we want to do. So first things first, let's go ahead and define the resultant velocity vector. So that information comes to us right here. We're told that the result is the plane of the plane and the wind. The result is the plane is flying 620 miles per hour due west. So if we draw that vector, here's to the west out here, right? So this vector is out to the west. That's directly west. And the magnitude here is 620 miles per hour. So if we break that down into its I and j components, the resultant vector is going to be equal to negative 620i, because all 620 miles per hour are directly to the left, plus 0j, because there's no up or down information. Okay, cool. Now let's go ahead and do the wind. So the velocity of the wind, right, we're told is 50 miles per hour east, bearing 30 degrees south. So that's going to look something like this. So it's going to be blowing in this direction. Maybe that's a little long, but that's okay. It's just a sketch. This is a 30-degree angle here. Or since we're defining it on the unit circle, we can define this as a negative 30-degree angle. And the magnitude of this vector is 50 miles per hour. All right, so then we want to break this into its components. So it's going to be the magnitude times the cosine of negative 30 degrees, which is going to be 50 times root 3 over 2. So 25 root 3i. And then we want to do the magnitude times the sine of negative 30 degrees. Sine of negative 30 degrees is negative 1/2. So 50 times negative 1/2 is negative 25j for that component. All right, so then we go back up here and say, what are we trying to do? Oh yeah, Vr minus Vw gives us Vj. So now let's go ahead and subtract these two vectors. So if we subtract those two vectors, that's going to give us the velocity of the jet. So doing so, we have negative 620 minus, since we're subtracting, minus 25 root 3 for our I component. And then we're subtracting the j's, so 0 minus negative 25 is positive 25. J is what the jets should be doing, which kind of makes sense when we think about this, right? Because if the wind is blowing south with a component that's south at 25 miles per hour, if the jet ends up flying directly to the west, then it must have a J component of positive 25 to exactly counteract this, right? Okay, cool. So we found the velocity of the jet. Now we need to figure out what the airspeed of the jet is. So we're just going to have to find the magnitude. So we'll say the magnitude of the jet is going to be equal to the square root of negative 620 minus 25 root 3. So the I component squared, plus the J component squared, 25 squared. And then we'll run this calculation. We'll put it all through the calculator. So I'm going to go, first I'm going to find negative 25 root 3. And then I'm going to subtract 620 from that. And I'll go ahead and square that right now. So then we get an approximate value, since I'm going to be rounding here, square root. So all of this stuff squared is going to be 439,968. 439,968.6, I'll call it. And then we're going to add that to 25 squared. So 25 squared is 625. So we'll add these things together and then take the square root of that. So add those two things together and we take the square root of that result. And we get an approximate speed of 663.8 miles per hour. I'll just round it to 664 miles per hour. So that's about how fast the airspeed of the jet is. So that's what the airspeed indicator should be reading, is that the jet is flying at 664 miles per hour. Okay, and now we need to figure out which direction the jet should be flying. All right, so let's go ahead and do that down here. So we're going to just sketch out this vector here. So we know that the I component is a negative number. So that's going to go out here. And I'll just label that negative 620 minus 25 root 3. And then the J component is, for the jet, positive 25. So those are the components. So then the jet is actually flying like this, right? And we're going to go ahead and solve for this angle right here. And so then we can say that theta is equal to the inverse tangent of the J stuff, 25, over the I stuff, negative 620, minus 25 root 3. And then when we run that through the calculator, so let's see, let's go ahead and run that through the calculator. So 25 root 3, and then we'll do negative 620 minus that answer. I want to do 25 divided by that thing, and the inverse tangent. And we get a tangent value of about negative 2.16 degrees. Now, we want to recognize that what that means is we're in quadrant 2 here, and so it's taking 180 degrees and subtracting 2.16 degrees back that way, right? So then we want to transfer this back to cardinal directions. So this is to the west and this is to the north. So then we can say that the compass should be reading west, bearing 2.16 degrees to the north. And this kind of makes sense, right? Because the jet is going super fast. The jet is going 664 miles per hour in this like north, well, in this west, a little bit north direction. The wind is blowing back against it this way and a little bit south, so that when the jet and the wind are acting against each other, the jet ends up flying directly west, a little bit slower than the jet is actually flying. Cool. So that's how we solve a problem like that. All right, let's do another one here. Let's look at this riverboat situation. So you just got your captain's license. Congratulations. To celebrate, you are taking your friends on a riverboat cruise. Now, here's what we know about the river is flowing at 2 miles per hour. The boat is capable of maintaining a speed of 7 miles per hour, and the river is 3 miles wide. So in this scenario, you wish to reach a dock directly across the river. You need to know what direction should your compass read as you cross the river. So let's take everything into account again. So we know that the velocity of the boat plus the velocity of the current in the river is going to equal the resultant velocity. So let's just take account of what we have here, the information we have. So we know that the river is flowing at 2 miles per hour in a direction that's downstream. So that is the current information. We know that the boat is capable of maintaining a speed of 7 miles per hour. So that's kind of some boat information, what the boat is able to do. You wish to reach a destination that is directly across the river, so directly across the river. So that's telling us something about the resultant vector. So now we have to be a little bit clever in how we set this up. Let's think about like what is actually the scenario that's occurring here. Well, so we know that the river is flowing downstream, is flowing downstream at 2 miles per hour. Right, so that's what the river is doing. And let me chart this over here. So we're gonna have the river that's going downstream at 2 miles per hour. Right, so here's the river's velocity vector, 2 miles per hour. And you wish to travel across the river. So you want your resultant vector to go straight across the river. Right, so let's say that you're over here and you want to drive straight across the river. You don't want to go up or down or anything like that. Well, you want your resultant vector to look something like this, right? You want to travel directly to the right. So what that means then is if we think about your boat, so your boat is capable of maintaining a speed of 7 miles per hour, but you get to decide which direction to point the boat, right? So maybe let's just think about if you were to point the boat just straight across the river and the current is pushing you down at 2 miles per hour, you're going to end up down here somewhere, right? Because you drove straight across, but the current pushed you down. And so we want to think about, well, when you aim the boat, you're going to have to point it slightly upstream in order to counteract the current, right? So this is going to be your total vector of the boat, but we want some component of that to be pointed upstream to counteract the river. And we actually know exactly how much of this 7 miles per hour, we know exactly how much of this should be directed upstream, because if we want to get straight across the river, we have to exactly counteract the current. So we need this to be 2 miles per hour. All right, so in order to go directly across the river, we need the boat to directly oppose the river in the J direction so that whatever's left over can be directed to the right here. So if this vector and this vector work against each other, then it's overall 0. So then the only vector that shows up is this one to the right, which is what we want. All right, cool. So now we just need to figure out what angle is that. Well, we have tools for that, right? Because we want to know what should this angle be. So looking at this triangle we've constructed down here, we have a reference angle, we have an opposite side, and we have a hypotenuse. So then we can say the sine of theta is equal to the opposite over the hypotenuse, and then solve for theta. So theta is going to be exactly equal to the inverse sine of 2/7. If we plug that into the calculator, the inverse sine of 2 divided by 7, we get a theta value of approximately 16.6 degrees. So then as you head across the river, your boat should be pointed about 16.6 degrees from directly across the river. So that should be a 16.6 degree angle there. Cool. And that's going to get us across the river. Now, we might want to know how fast are we going across the river. Well, that just means we need to solve for this side of the triangle. So we'll use Pythagorean theorem for that, right? So we'll say 2 squared plus x squared equals 7 squared. And then we can solve for that missing side there. So we'll have 4 plus x squared equals 49. So x squared equals 45. And then we take the square root of that. So that's going to be 3 root 5, or the square root of 45 is approximately equal to 6.7. So 6.7 miles per hour is how fast we're traveling in this direction to the right. Cool. That's going to become important in the next question. So we know we're traveling at 6.7 miles per hour to the right. So we just found that out. So our travel across the river here, let me sketch that in. Our travel directly across the river is at 6.7 miles per hour, which is important because now it's saying the river is 3 miles wide. How long will the trip take? And we just have to do some dimensional analysis here because we know the boat is capable of traveling at 6.7 miles per 1 hour. So we can set up a ratio and say, well, that's equal to, if the river is 3 miles wide, then we'll say it will take us X number of hours to reach the other shore. And now we can cross multiply. So we have 6.7x equals 3, divide by 6.7 on both sides. So we get X is equal to 0.48, we'll call it. So 448 hours, which is cool, but nobody really talks like that. Nobody says 0.448 hours. So then if we want to turn it into minutes, we'll say 0.448 hours. We can convert this using some dimensional analysis, where we know that in 1 hour, there are 60 minutes. And when we set it up like this, hours cancel out. And so then we can do 0.448 times 60, and then technically divided by 1, and we get 26.7 minutes. So we'll make it across the river in approximately 27 minutes. And that is that. Cool. So that's what we want to do with velocity vectors. And yeah, it's important to conceptualize the situation first so that you know what you're solving for. Plug in the information that you know, and then back out the information that you're trying to solve. If you have any questions, drop them in the comments, and I would be happy to answer them. Stay tuned for the force vectors video coming up next. Thank you.